Okay, thanks for everybody coming tonight. Welcome to the March meeting of the Chemical Consultants Network. I'm Mike Michalczak. I'm the chair of CCN. Chemical Consultants Network is a group of chemists and chemical engineers that advise members who are consulting or interested in consulting. We provide expertise and resources to our members. We're a topical group of the Philadelphia section of the ACS. We're also supported by AICHE. We hold monthly meetings on topics of interest, as you are all here tonight. And for $35 per year, paid members can create a web page on our website, track potential clients. You can sign up to be a member at chemicalconsultants.org. Also, Joanne wanted me to point out that these videos, all our meetings are being videoed, and they'll be on our YouTube channel. So check out our YouTube channel if you miss a meeting and you want to see a past meeting. So our speakers tonight are Dr. Ron Bihovsky from Key Synthesis and Dave Vahlsing from Becht Engineering. And they're going to talk about how to have effective collaboration between scientists and engineers. And if anybody, I'm sure everybody on the line is either a chemist or an engineer or maybe a life scientist. And we all know that there's a different mode of thinking between the fields. And any scientist who's worked with other people, even marketing people or regulatory people, you need to work effectively with people from other technical disciplines. So tonight, Ron and Dave will give us their thoughts on how to have engineers and scientists work together. Give you a brief bio. Dr. Ron Bihovsky is an organic chemist. He's a consultant, founder of Key Synthesis. He's also a past chair of CCN. Dave Vahlsing is a chemical engineer. He's worked at various positions throughout his career in the chemical refining industries. Dave was a co-founder of CCN along with Bill Galton and is currently a manager at Becht Engineering's Philadelphia office. So Ron, Dave, I'll let you go.
So as everybody knows, the title of the talk is Effective Collaboration Between Scientists and Engineers, or I think most of us are chemists, so you can substitute the word chemist for scientists. And I'll be talking as a representative, as Mike mentioned, of the synthetic organic community, and Dave will be talking from a perspective of a chemical engineer. I formed Key Synthesis about 20 years ago, about the same time I joined CCN. Key Synthesis is a custom synthesis laboratory located in the Philadelphia region. And I like to say we do small-scale synthesis. In reality, the truth is I do small-scale synthesis. It's a company of one. I'm the president, and I take out the garbage. We do small-scale synthesis of biologically active compounds, usually on a pretty small scale. It's organic chemistry. And I do a reasonable amount of consulting for the pharmaceutical, biotech, and intellectual property areas. Just a very brief list of my experience. I have a PhD in organic chemistry from Berkeley. I was an NIH postdoctoral fellow. I was an assistant professor at Stony Brook University and worked in the pharmaceutical industry for about 15 years until founding Key Synthesis, as I said, about 20 years ago. So getting into the topic of the talk, what is this little thing? I'm sorry about that gray space there. I'm not sure what that is. I see. It says move it away. Oops. Yeah, I'm having trouble with this. Everybody see this gray or black box?
Mm-hmm.
Yes.
All right. No, it's
fading now.
So chemists and chemical engineers have different vocabulary, different concerns. On the left side, chemists tend to work with whatever equipment is available in lab. I mean, in my lab, I have all the equipment I need to do syntheses on a milligram scale to several hundred gram scale. Just take it off the shelf. Chemists tend to think in chemical equations. chemical names, that is the names of the chemicals, reaction names. Some reactions have names like Grignard, aldol, cannabinol. We think in terms of reaction mechanisms, particularly to determine what, if there's a problem in a reaction, how to get around the problem and improve yields, improve conditions. Chemical engineers tend to deal with specialized equipment. Sometimes it is equipment that is devoted to a particular process. Chemical engineering is a lot more mathematical, deals with certain equations and problem solving frequently through mathematical manipulation. There's a difference in the definition of a good process. I think most chemists would be happy with a reaction that gives a 90% yield and reasonably happy with one that gives, say, a 60 or 70% yield. When chemical engineers get involved, they would probably prefer reactions that give close to 100% yield and are easy to carry out on a routine basis. Chemical engineers speak in terms of process flow diagrams and flow summary tables and rely on those extensively. I'll talk about those in a little bit. And there's also a question of return on investment, cost-benefit analysis. When a chemist is looking at a reaction, generally it's just to make a reasonably small amount of material, and there's really not a cost-benefit analysis involved. Again, a chemist will work on a small scale, typically grams. Yields are somewhat important, but not necessarily a focus. And particularly in medicinal chemistry, the initial synthesis of a compound could be just milligrams of material. That might be all that's necessary for testing whether the compound's biologically active. The synthesis may not be at all optimized or ideal, and sometimes totally new syntheses might be required. Chemists tend to study reactions, hypotheses. As I mentioned, use whatever glassware is available. Stirring can frequently be magnetic. That's relatively easy to set up, and also easy if you have to conduct a reaction under an inert atmosphere. Mechanical stirring certainly can be done, but it's a little bit more time consuming to set up. Purification can be by chromatography. A cursor here, this is a chromatographic column. White material is silica gel, and the red material is the material that we're trying to isolate and purify. Chromatography is great for small scale purification of, let's say, a couple milligrams to a couple grams. But beyond that, it's something that we try to avoid on large scale. Recrystallization is much better for large scale, and distillation if the compound has a low enough boiling point. There's certainly some safety and toxicity issues, but they're relatively minor compared to when reactions are conducted on a very large scale. So chemical engineers tend to work on a large scale, frequently tons or even multiple tons. Yields are important because every little bit increases the economics of the process. Chemical engineers like to deal with high concentrations of reactants because solvent is also expensive and has to be either recycled or disposed of. There's large dedicated equipment, certainly large equipment, often dedicated. Stirring has to be through mechanical mixers, and chromatography, as I mentioned, becomes somewhat impractical to totally impractical. Certainly on a ton scale, it would be totally impractical. Material transfer, I'll go talk about in a minute, but that means transfer of solid materials, solvents, or solutions, or even gases from one place to another. Chemical engineers have to be concerned about heat transfer and energy use, particularly on a large scale. Exothermic or endothermic reactions are something to certainly be concerned about. And even though safety and toxicity are important on a small scale, on a large scale, obviously disasters can happen and they have to be avoided. Risk management is related. Getting rid of waste and environmental concerns are important. And again, the economics or return on investment is
And ignore if you think that I don't want to upset him, of course, but he does get into. Yeah.
So,
yeah, I understand.
Joanne,
Okay.
can you help me remove the black box? I
Yeah.
don't know where it came from. If not, we'll just have to look through it. Oops. Yeah, I'm having trouble moving it. So, illustration of the magnetic stirring issue. The picture on the left is actually from my laboratory. It's a 2-liter flask with about 1 liter of
Okay.
in it, and stirring is magnetic. This is about as large a scale as you can use for stirring. Any larger in the stir bar tends to not fit the stir. So the diagram on the right here is a 100-liter stainless steel reactor, and the blue apparatus at the top is a mechanical stirrer.
Hey, Ron,
Yes.
could you pause for a moment? There's this box that, first of all, Joanne sent a note to Mike who didn't pick it up. She can edit this section out of this little sidebar. Why don't you take the time to get rid of that window? It really doesn't need to be there.
Get rid of this window.
There's a box that goes from R to manufacturing's A.
Yeah, I can see the box, but
There's another window on your desk that should be showing on your desktop that it looks like it's Zoom that might be objecting to the positioning of it. I personally haven't seen this before, but if you can just look to see if there's another window, and I would just minimize it to get it out of the way. If there's anything else running on your desktop.
right.
Or can you click and drag it?
No, it won't.
You can't minimize it either.
No.
Can you see it?
Maybe stop share screen for a minute and then you could sort it out and then go back to share screen.
Okay.
You might have accidentally gotten 2 screens or something. Also, somebody was not muted and they were
On the phone. Yeah,
adding unattractive sound.
yeah.
Think
Please
that-
mute your mics if you're not speaking.
I think that was David Vahlsing.
So the slide that you were on, once you get this puppy cleaned up, if you could just pick up from the beginning of that slide, because that's when the talking started. Don't you just love technology?
You're good. Yep.
Maybe it went
Go on.
away.
I did it by accident. Sorry.
You fix it? I think you fixed it.
I didn't do
Yep,
anything,
done.
but it looks better.
Looks clean.
Okay. Yeah, I was talking about mixing, mechanical
I'm out. Everybody mute, please.
mechanical mixing.
Ron, Hey, Ron, if you could do me a favor and just do like a 3, 2, 1 countdown so that I know where to pick
Sure.
up the edit again.
Okay, 3, 2, 1. So as I was saying, mechanical stirring is really typically necessary for volumes greater than 1 liter. And it's back again. And the illustration at the right is a 100-liter reactor with a mixer affixed to the top of it. Sorry about the box being back again. I don't know why that's happening. This is a pharmaceutical manufacturing plant, and you can see it looks a lot different from the kind of equipment that we use in a organic synthetic laboratory. So this is where the chemical engineering really comes in. This is just a typical process flow diagram that I copied out of a textbook. This is typically what chemical engineers use to keep track of the equipment, which is indicated with the various round and oval shaped, etc. symbols. And the lines with arrows indicate the flow of the solutions and reagents. Another typical tool is this flow summary table. This includes the composition and process conditions for each stream, typically liquid, but it could be gaseous streams. So they, in this case, are numbered 1 to 10. I've seen cases where there are hundreds of different streams, and each stream is characterized by the temperature, pressure, in this case, vapor pressure, the amount of material in terms of grams or tons, or the flow in tons per hour, and what the composition is, in this case, hydrogen, methane, benzene, toluene. Material transfer I touched on a minute ago. Again, that means transfer of material from one place to another. It could be a solution, it could be a solid, it could be a solvent. And a typical situation is that a chemist does reaction on a reasonably small scale, and in the end has the pure product and removes the solvent that it's in and generates what I've shown here on the right, the material as a solid inside the flask. The process can be transferred to the pilot plant, and the chemist gets a call from the pilot plant. The pilot plant operator says, "How did you remove the solvent from your flask?" And the chemist responds, "I scraped it out with a spatula." To which the pilot plant operator says, "Well, you better get over here right away with a 6-foot shovel." So the lesson from this is that what works on a small scale for a synthetic organic chemist is not going to work in a pilot plant or certainly in a manufacturing plant. So I want to go through briefly 3 projects that I've been involved with at Key Synthesis: the extraction purification of a natural product, a pharmaceutical synthesis, and a chemical synthesis example. So starting with the natural product, I was asked to consult on a situation where a natural product was extracted from a plant and purified by recrystallization. Pretty simple standard process, at least on a small scale. The chemistry on a small scale was very well known for decades. A chemical engineer extrapolated the small scale process to a large scale process and designed a multi-ton plant, which, by the way, was never built. And the question was, is this intellectual property, or is it just a scale up? The chemical engineer had to deal with purity because this was going to be natural product was going to be used in a pharmaceutical setting. The efficiency of the process, heat transfer, energy requirements, material transfer, mixing, safety, recycling, waste management, equipment, specialized equipment, plant design and construction, and cost benefit analysis. So again, my role in this as a chemist was to provide my input about whether this chemical engineering input amounted to an intellectual property contribution. Pharmaceutical synthesis example. I've illustrated at the top one of the simplest examples that you can imagine. It's the coupling of the compound on the upper left, which is a benzoic halide, where X is a leaving group, with a phenol that is done in the presence of base to produce an ether. So it's a halide plus phenol gives an ether. The complication here is that the starting materials are quite costly because of the R and R prime groups. They have other functionalities, so side reactions can occur. And they are, did I say this already? They are quite expensive. So considering that they were expensive, I did some preliminary experiments on a 100 milligram scale, a 0.1 gram scale, eventually scaling up to 5 grams. Originally, I utilized the very expensive but commercially available benzoic bromide, which was also toxic, unstable, and I could tell was a skin irritant. The base that I used originally was sodium carbonate. I eventually used diisopropyl ethylamine. Sodium carbonate is not a good base to use on a large scale because, first of all, it generates lots of carbon dioxide, and secondly, it's not homogeneous, so the reaction has a tendency not to be reproducible. I got about an 80% yield after recrystallization, 99% purity, no obvious impurities by NMR or TLC. The solvent that I used was originally DNF, but there's a concern, the FDA is concerned about nitrosamines, which are potentially carcinogenic. So we shifted in the pilot plant to acetonitrile. In the pilot plant, it was done on a 7 kilogram scale. We utilized the benzoic chloride with catalytic potassium iodide that transiently forms the corresponding iodide. And the advantage is that the chloride is much less expensive, more stable, less toxic. They used isopropyl ethylamine. We get a 70% yield after recrystallization, and HPLC showed 99.7% purity, which is sufficient for a GMP block for the FDA. And finally, I'd like to speak about another synthetic chemistry example. The idea was to prepare this compound in the upper right. It is an alpha beta unsaturated aldehyde. It is commercially available. It is commercially available, but we needed to get a very inexpensive synthesis of this compound. So I spent about 9 months, not full time, but 9 months doing experiments to synthesize this by total synthesis, kind of from scratch. And had lots of ideas, but the yields were generally not sufficiently high. So eventually I settled on oxidizing this allylic alcohol, shown here to the left, to the corresponding aldehyde. And that was done on a 1 gram scale to find optimal conditions. Some of the oxidizing agents considered, one was chromium trioxide. This would be a typical way that an organic chemist would oxidize an alcohol, but it's really not acceptable on a large scale because chromium is highly toxic and carcinogenic. Manganese dioxide gave a decent yield, but you have to use a tremendous excess of manganese dioxide, so that was rejected. We tried using DMSO, dimethyl sulfoxide, as an oxidizing agent with a couple conditions. Neither of these gave an acceptable yield, and you have the other problem that DMSO in the process is reduced to dimethyl sulfide, which stinks. And on a large scale, that would be certainly unacceptable. We became interested in oxidations using tetramethyl piperidine oxide as a catalyst. And one of those involved using sodium hypochlorite as the oxidant, which is bleach, so it's quite inexpensive. It gave a 39% yield, but the product was impure, and the reason is that you get sodium hypochlorite adding to the double bond, so there are lots of side products involved. What attracted our attention was a catalytic use of tempo plus copper triflate, bipyridol, and N-methyl imidazole, and those are all in catalytic amounts, and air at 1 atmosphere is used as the oxidant in acetonitrile or dichloromethane. And we got from 55 to 79% yield after distillation, 95, at least 95% purity. This looked pretty good, except that some of the reagents, even though they're catalytic, are somewhat expensive for this product. They had to be made economically. The other thing is that we noticed a slight exotherm on a 1 gram scale of about 4 degrees, starting at room temperature and increasing 4 degrees. So as you increase the scale, that's going to be more of an issue. And again, the product was purified by distillation. So we turned this over to a pilot plant and a kilo lab, I should say, and got some chemical engineers involved. We identified more economical catalysts because, again, cost was critical. We tried to decrease the amount of catalyst down to a very low level. The reaction was exothermic, but that wasn't a problem. We could conduct the reaction at a higher temperature. We tried to decrease the concentration of solvent, which worked fine. And normally I wouldn't even try this, but we conducted the reaction neat without any solvent at all, and it worked great. Also, rather than using air, we utilized pure oxygen, and we used an autoclave to do it under pressure. There's some concern about combustion or explosive hazard, but that was measured using calorimeters, and everything fortunately worked out fine. In the kilo lab, they get a 91% yield, and the product was purified by distillation to a purity of greater than 95%. So it worked in the kilo lab, being transferred to the pilot plant, and everything looks pretty good. So in conclusion, chemists and chemical engineers can work effectively together to solve challenges, but they have to understand each other's vocabulary, concern, thought processes. So that's about it. I wanted to turn it over to Dave Vahlsing, who will discuss this discuss the topic from the chemical engineer's perspective. And by the way, if you have any questions, I think the best way to handle it is we'll take them at the end. You could either unmute at the end or send questions through the chat application, and Michael will read them off at the end. Thanks for your attention.
Okay, I am a chemical engineer. I did my studies at MIT. I am a professional engineer by exam. I'm giving you a little background because this might lead to an understanding of how chemical engineers work with chemists. I did spend 33 years with Sun, both at refineries, central engineering in Toronto, corporate headquarters, and then the last 10 years in R&D. I was downsized, as many people from Sunoco and DuPont were. And when that happened, I formed Hydrocarbon Engineering Associates with two men who were in R&D with me, Fred Camp and Ebe Steinmetz. The company was acquired by Becht Engineering in 2003. I am a founder of the Consultants, Chemical Consultants Network, along with Bill Golton. We met many years ago at the White Dog Cafe down at Penn, our first meeting. Now it isn't changing the picture for me. What the heck has happened now? I'll do it this way at the bottom. Okay, what is a chemical engineer? I say not even chemical engineers know. Now that's not entirely true. It's they don't know what they want to do when they become chemical engineers. I was asked to speak at Penn State University a number of years ago on a course, a required course called Orientation to the Profession. It's now called the Professional Development Seminar. And it was required for third-year undergraduates and all graduate program chemical engineers. And the purpose of it was to tell people what might we become. Of course, directions for engineering are varied. They could be law, medicine, sales, process design, which is what I talked about. You could, of course, stay in academics, pharmaceuticals, tech service, energy, consulting, and or research support in R&D, which I eventually did. So how did I get there? How did I get trained so I might be useful in R&D? While I was still in college, I had a summer program at Marcus Hook when the company used to evaluate crude oil by tearing it apart, because each crude oil is like different fingerprints. In fact, the same crude from the same hole in the ground can change over time. So I spent a summer there, great opportunity to learn a bit about organic chemistry. After I graduated from Sun, I spent 2 years in Toledo at a refinery. They gave me the first 6 months in the refinery lab to learn the testing for quality control. That was the main thing in Toledo. They did not have an R&D. Then I came to Philadelphia to central engineering, and they gave me 4 months in technical economics, where cost estimates on plants, cost data for older plants were kept to help to figure out what is a new facility going to cost. I then spent 15 years in process design and technology evaluation, and my last 11 years in R&D, where I was in charge of a group that supported the tar sands facility up in Alberta. We did some research for the Air Force, and we did a project. Now, how does this all make me any good for R&D support? Well, maybe the best way would be to get a PhD with an emphasis on research. That was not me. I did not do that. So let me talk briefly about a real project. Many reactions require a catalyst. Sometimes they're dangerous, specifically hydrofluoric acid, which is used to convert a couple of small C4 molecules into a C8, which I'll show you the formula for in a second. So the dream of Sun was to have a catalyst that did not require high temperatures, which is often the case, or pressures, or conditions that would be more risky, or a catalyst like hydrofluoric acid. So Sun's chemists and engineers and techs developed a solid superacid catalyst in the lab, and they were encouraged by what they saw. So we built a small pilot plant, was located out in the refinery, operating on a normal butane side stream coming from an alkylation unit. We ran this thing around the clock for about 4 months, gathering data on catalyst life and conversion. So briefly, at Ron's suggestion, he said, let's see a molecule. So normal butane over this catalyst is converted to isobutane. Now, why? What's the interest in making that conversion? Well, part of it's just straight economics. Normal butane, which is often put in to vaporize gasoline for certain seasons, you use it as a fuel component. But isobutane is more valuable. I looked up some data, and in 2010, roughly, isobutane was worth 20% more than normal butane. Last fall, though, it was only a 5% difference. So if you're using large quantities of the material, it could start to add up. So what do you want isobutane for? Well, it turns out in the alkylation process, and the current catalyst for that are sulfuric acid or hydrofluoric acid. If you combine isobutane with isobutylene, you come up with something called 2,2,4-trimethyl pentane, which is isooctane. And when the first measurements of components that could give you good octane were made, isooctane was thought to be about the best you could get. It's roughly 100 octane. And the scale when they used to measure octane was you'd have in a test device, you blend octane. The lowest number, which was thought to be like roughly 0, was a straight chain. You blend these in proportion and test them in a test engine against the materials you made. I'm digressing here. So we built this pilot unit. This is not the pilot unit. I could not find the photographs that I took, or probably shouldn't have taken, but this is a picture of one roughly the same size. And this was, as I say, out in the refinery, running around the clock for about 4 months. So what happened? Well, it turns out our active catalyst did not like feed impurities in the refinery source butane. And the cycle life on the catalyst, the solid catalyst, was not great. It could be regenerated. But of course, every time you regenerate a catalyst, it gets less and less active. It's very difficult to get back to original activity. Now, here's a little side thought. It's obvious now, but we should have drawn samples from the refinery streams instead of using pure normal butane for our tests in the lab. A lesson for us. Well, what happened, as I say, what happened? Management decided to terminate the project and basically forego long-term research, instead buy technology. I mean, it takes a decision to hang in for a long time if you're going to do research of this nature. They shut down all long-term research, retired engineers and chemists. I was one of them, which led me to founding my own consulting company with Fred Camp and Eve Steinmetz. But the good news is the technology did have value. It was sold to a technology development company, and the company is to recover the investment on put into development. And my understanding is that it has since been commercialized. This is a nice little gift. Sun, when it was into patents, we had several patent lawyers. So Sun was into getting patents, and they were nice enough to recognize anybody who got one. And I got this beautiful plaque. What I'll do with it, I don't know. If the pilot plan had been successful, what happens? Well, if it had been, we would have kicked into using new chemical engineering skills, such as what is the investment going to be for a full-size plant, both manpower and hardware? What would be the return on investment? And of course, that would depend on the price of feedstock, byproducts you might make, and the product value. And then, of course, competition from other corporate projects can always stop projects from going ahead. There may not be enough money to go around. At that time, well, actually, in the early days, Sun did not borrow money. They self-financed. But since that time, many companies go out and they borrow money, but you'd still have to make a good case that this had a good prospect. The engineering people would also address scale-up issues with working with the chemists and begin to design full-size equipment, which would require heat transfer skill, fractionation, hydraulics, instrumentation, and of course, concern about safety. So what makes for a successful project? Manoj Bindi is a PhD chemical engineer, also worked at Sun at the same time I was there. And I called him and I said, what do you think? In fact, he's the man that packaged up what was left of the technology, the superacid technology, and helped get it sold. He pointed out, these are almost word for word comments from him. Engineers should get involved early. Bench scale testing should involve a lot of back and forth between chemists and engineers to fine tune the catalyst formulations and develop and move toward a lab from the lab scale. Chemists should be involved early in the pilot unit design to accommodate requirements for catalyst handling and maintenance. And then, as I mentioned earlier, commercialization of the technology depends on successful pilot plant demonstration and also has to fit whatever the criteria are at that time for the company. And again, it depends on fighting for the funds, competing against other possible capital needs. A few years before I retired from Sun, I attended a 3-day course that was given by an outfit called Industrial Research Institute. And what this was a gathering of people from R&Ds from all around the country, different businesses, and they were to share ideas about what they felt made for successful projects. And these are some of the so-called pearls that came from the participants. Technology transfers a body sport, meaning the chemists and chemical engineers and mechanical, everybody needs to work together. Communicate bad news face to face. If things aren't going well, you better speak up. Call on upper management clout if you want the funds and you want to keep going. Certainly understand customers' needs fully. Suggesting bringing in independent experts at the final stage of design. Don't be convinced by those who are too close to it that everything is good. Test the proposed changes in the commercial unit in the pilot unit first. If you've got to modify the full scale design, check it out in the pilot unit. And another gem was give inventors real world experience to avoid impractical results. Now, this Industrial Research Institute still exists, but they've changed the name. It's now called the Innovation Research Interchange. Same initials, but they've changed the name. I just went online to see if they still did exist. But this would be a great thing to be a member of if you wanted to compare ideas on what works. Sorry, I'm losing my voice, folks, but that is it for me.
Are there any questions? There's nothing in the chat, and anybody else has a question, please speak up.
Well, yeah, I got a quick question. Can you guys hear me?
Yes.
I
Okay,
can.
I got a quick question. In order to be a really successful chemist, in order to be considered to be top of your field, you need to be, I think most people would agree that you need to be a PhD, but that is not necessarily true for the chemical engineers. What is the difference, substantial difference between the chemical engineers with a BS and with a PhD?
Well, not if you want me to try to answer. I'm not a PhD, but
Right. Yeah, I understand that. But I mean, you having just a BS has never held you back, right?
Well, it hasn't, but we weren't successful in this particular case. But I think you could say we gave it a good shot. We didn't get into a full scale up, which I think I could have, or with the right people could have handled. We just weren't lucky in terms of catalyst and time to develop it.
Right.
But to answer your question, that's why I tried to give some examples of some of the things that perhaps helped provide me with some background. But as a chemical engineer, you really don't learn the business in school, even if you had a PhD.
Yeah.
You have to go out and have mentors, people that help teach you. I mean, in central engineering, I was a young person, and I would not have succeeded without the help of more mature engineers in various fields, not just chemical engineering. But you don't come in out of school and make great strides. You have to learn the business. So I don't know if I'm answering the question. I'm kind of babbling here, but
Can
our whole
can I chime in here a little bit? This is an interesting thing, and maybe Dave, you don't remember that, but at the time I was at the running the Tulsa refinery, and you came out because we had a spare unit, and that could potentially take this catalyst and run it on essentially refinery feedstock. But I think there was a situation on the funding of running that particular operation. I had the manpower to do it, but the fact is, it was some other thing, and it basically it fell through. I don't remember coming out to Tulsa. It was probably back in it must have been in the early late 80s. Do you remember that?
I don't, but that's because my memory's gotten very fuzzy.
Yeah, right.
But I think it probably had to do with the fact management just wasn't ready to go
to do it, right?
Yeah.
So let me take a stab at this question. It basically comes to essentially how many times you've been around the block. A lot of times you'll have a PhD chemical engineer, in many cases, will be normally shunted out in a particular field, and they'll stick in that field because of their knowledge of that area. They'll stick in that area. For Dave and I and a lot of other ones who are, let's say in BSMS type degrees, well, basically have been around a number of different disciplines in the chemical engineering field. So we've touched a number of things, and that can be very useful. I think as I said, I was commenting on this with Dave, having a look at over the slides. I would say that for the chemists, the interchange is going to be important because as mostly for us chemical engineers, we don't really know all the intimate details of the catalyst chemistry. The transfer of the particular electrons, or how this is going to work, or what happens here on a particular surface, if it's rhenium or a mixture of rhenium, platinum, whatever you're going to be using. And to that extent, that has to be known. Second of all, most chemists don't know unit operations, which are the large-scale equipment necessary for a lot of this stuff. Now, this may be different for, I don't know, did I disappear on a different screen?
No, you're still there.
I'm still there. Okay. This may be different in the pharmaceuticals if you're using. There's a distinction between batch processing and, I say, continuous processing. And batch processing is going to look more like a pilot plant, just bigger, and you can relate to it. So you'll have batch distillations, you'll have this and other things that are batch related. Continuous is usually a whole different ball game because you're operating essentially 24/7, 365, and you have to take advantage of that. An important thing that Dave was mentioning is a lot of times the feedstocks that the chemists are using for the synthesis will have to match what's available if you start buying it in bulk. And a particular problem came up, and this was when Sun was involved with manufacturing, and now a four-letter word that's probably can't be used in polite company, was MTBE. And MTBE had to do with essentially, they were taking essentially a stream of butanes. I think this was, it could be, I think it was an iso stream, circulating. And they were going to essentially try to use a the amount of there's a circulating stream in the Houston area that everybody puts in their stuff that's basically from I'm sorry, normal. It's normal butanes that are basically reject from refinery alkylation operations. That looked like the ideal feedstock, but it could not be used because there were impurities in there, such as HF, trace amounts of HF or sulfuric acid, which were used in the catalytic manufacture of what Dave was trying to do here, making isooctane in what they call an alkylation process. So that plant had to be spotted in an area which is called Mount Bellevue, because it's the only place that we basically had what we call virgin C4s that did not have any, had not gone through any processing. So, and that has to be known though, because that can really affect your economics. So you have to end up knowing and knowing that ahead of time would be really important. So I think the question there is that the chemist has to explain to the chemical engineer how the reaction works, what can be done as far as if you try to do it in either batch or continuous. I can't speak anything for pharmaceuticals here. I don't know anything at all, but for just the chemical operations. And then for the chemist has to understand if this is going to be profitable, X amount of tons of this stuff has to be made, and it's going to be done in this type of process. And here's the economics of it. And that's my 2 cents.
Arvo, I'll mention one thing that Ron mentioned that is not at least my experience, and that is there are very few batch operations in refining, which we're most familiar with.
Right.
Almost everything is continuous.
Right.
And we don't get 100% yield. We
No.
recycle the components that don't react. So you do get yield up that way, but we seldom see any reactions that are 100%, and we seldom see batch operations.
And the recycle stream, handling recycle streams is also important in that pilot plant operation, because a lot of times spinning that stuff around, can kill you. All right, so you have to be very careful on how much you're going to take and how much you're going to reject, and that's all part of the economics. So I don't know if we did anything here. Go ahead.
No, but what I was going to say is kind of building on what you said is what I've learned in interacting with chemical engineers, and actually it's across the board, whether it's marketing people, regulatory people, or whatever, is you got to understand how they think. You have to understand their language.
Yeah, marketing people are kind of low on the scale.
Right, because understand their language, I think it helps a lot in the communication.
Correct.
Yeah.
Because there's a lot of things where in my career where if I understood how a regulatory person thought or a marketing person thought, the communication would be a lot better. And I think understanding the way other people speak, their nomenclature, their language goes a long way to understanding what they view. I mean, I'll just give you a short thing. When I was at DuPont, I was working in a ceramics group, and I was making materials with chemical techniques. And I made something with a Grignard, a typical chemical reaction. And I gave a talk, and the ceramist said, "What's the magnesium impurity in that?" And I thought, huh? And apparently trace ppm magnesium had a real detrimental effect on ceramics. And as a chemist, I just shake it up and I get rid of the magnesium. But in a ceramics point of view, that was an impurity which really caused grain boundaries and caused defects in ceramics. So you got to understand how the other person thinks.
Right.
Yeah. So actually, I'd like to broaden the discussion just a little bit. I'm speaking from the perspective of an industrial biochemist. So although I know enough a little bit of synthetic chemistry enough to be dangerous about how people think about scaling chemical reactions up as well, I would say, and I'd like to sort of test drive this thought with the rest of the audience, it's so important for the scientists, whether they're life scientists trying to scale up a bioprocess, which we're trying to do now, or chemists, to be able to speak with the chemical engineers at an early stage. Because something I'd like to test drive with you folks is we scientists are usually able to call upon so many different reagents, so many different reaction conditions, so many different reaction vessels, control our reactions, whether it's bio or synthetic chemical, and have a variety of tools available at small scale. And then as the scale goes up, chemical engineers impose themselves, and rightly so, say, well, do you realize that you can never afford those reagents, or do you realize that you could never afford to do this type of mixing, or do you realize that you could never afford to eliminate this impurity from the reaction? And we oftentimes are, as scientists, find that out later, whereas if we'd communicated earlier, we would have understood a little bit better the practical constraints in the scale up. And that's not to say that we shouldn't challenge chemical engineers, because if the chemical does something extraordinary, like I don't know, solves, cures breast cancer at really, really low levels, then it's worth it to challenge chemical engineers to try to get the reactions. But you understand this tension, and perhaps the audience would like to talk about that.
Yeah, but that's right, Keith. But then the earlier you get that conversation going, the better chance you have of solving it.
Right.
That's a good point. And I would just go back to the example that I have of the oxidation that was eventually done with air, tempo, and some of the catalysts. The chemical engineer that I was working with, well, first of all, I could buy these compounds, the catalysts, from Sigma Aldrich or something like that, and I knew what the prices were. The chemical engineer was able to quickly find out what the actual industrial prices were for large quantities.
Mm-hmm.
And he constructed a chart saying, this is how much each one of these is going to cost, and it has to be a lot less than the price that they could charge for the final product. So it was very instructive.
Mm-hmm.
Well, the quicker you bring on a chemical engineer into a project, the more you're going to avoid embarrassment. I mean, when I worked for Carbide, you tended to act as a team, one chemist, one chemical engineer. So if there were problems, they were caught in the bud. I was working on one project. We were making a caprolactone-based monomer for cars. And so I spoke to the chemist, and she went over the reaction with me. And said, there's only one bad problem. I said, what's that? Oh, it tends to run away and plug. And I said, how often?
That's the problem.
I said, 50% of the time. And I said, what do? I throw out the flask. And I said, well, I can't throw out a 100-gallon stainless steel reactor. So when you have a reaction that's like 90% without plugging, 10% failure, we can start talking.
Exactly.
But imagine if she went down the road and at the last minute said, oh, by the way, we put 50%. That would have been a disaster.
Mm-hmm.
Yeah. Well, Ron, just talking to you, you talked about that oxidation. If you're dealing with pure oxygen, bench scale situation, you can probably do that relatively easy because you've got a short run of stainless between your oxidation supply and your reaction. But if you're doing that in an industrial area, you got to be damn careful on how you do that, because if you have any kind of impurities in a situation with pure oxygen, okay, you can come up with a real fire hazard very fast. So and those things have to be laid out, ahead of time. So if you're going to do that, it's doable. You just have to make sure that gets into the design, because if you come in otherwise, you can't just add it on. We saw a plant where they tried some of that stuff. Amazingly, it didn't work. So the fact it was abandoned, and thank God it was abandoned. I won't go into it. I won't name any names here. Huh?
At that point, we were certainly concerned about using pure oxygen.
Yeah.
And so far, so good. They did calorimetry and didn't find any combustion or explosive characteristics.
No, this guy's trying to run pure oxygen in regular steel lines. Okay. So if you got any moisture in there, you got any rust. Okay.
No, that's a good point. The disadvantage of using air is that what's the oxygen content? 18%?
21%.
21. Thank you. So you'd end up exhausting all the oxygen in the air, but you still have about 80% of the pressure would be left. Then you'd have to evacuate and repressurize with air.
No problem. It's just one of those things you have to end up getting a chemical engineer and chemist in there early, so the guy says, okay, I can design with this in mind and we're not going to have an issue. That's all.
Yeah.
One of the things that also has to do with the management, because when I was a chemist working in an industry, I came up with a really neat process, and it solved a huge problem from a chemist's point of view. And I said, wow, this is great. We're going to get patents on this. This is going to make us so much money. And of course, and I brought it to and to my boss, and he said, oh yeah, that's great. And then we threw it over the fence to the engineers, and they said, this is ridiculous. We will not be able to do any of this. You have not just oxygen, you have like a hydrogen stream coming off, and you have explosives. It's never going to be able to work. It was actually it was a very neat thing that I came up with, and my management has spent significant amount of time, of my time, my team's time, but unfortunately, it didn't work, or it did not go anywhere because of the problems with the engineers. And the lesson I've learned is that even though your management may support you as a scientist, it may be better for the company if they are not as being encouraged or as being encouraging for the chemists or the scientists that early on, and give more of a constraint as what the problem you're trying to solve. Because in my view at that time, I naively thought, well, I did everything right. I should be, I feel rewarded for this. And if it doesn't work, well, that's not my problem. I did my things. It's the engineer's problem.
Peter, I'd like to add a comment. Excuse me, Arv, because it connects to that. The chemist that developed the chemistry for superacids was Joe Shue, who we became very good friends. We worked together. We actually went to Manchester, England. The catalyst base for this superacid was zirconia. And we actually approached a manufacturer to get quantities that we thought we would need if we went commercial. When this project died, because management said it was going to die, he was so upset. He could not believe it because he had a great idea. It seemed to be working in the lab. And when the company shut it down, he was almost beside himself. As you say, Peter, it's a great idea. He was so excited, and then it could go nowhere. And it wasn't his fault. It was just the company couldn't continue, decided not to continue.
Yeah. So on that, Dave, thinking about what I proposed or talked about before, I don't think it is a bad thing for scientists to challenge chemical engineers. There should be a healthy tension between the two. If the molecule or the process or the bioprocess that the scientist comes up with at the lab scale looks to be valuable enough, there shouldn't be a problem with an organization challenging its chemical engineers to try to do something innovative. However, I will always agree that the chemical engineers in general will tell the scientists, whether it's a chemist or a biochemist or whatever, this is the known set of conditions, the known set of equipment. These are the known constraints. These are the reagents that we know right now to be economical. And then plug that into the techno-economic analysis. Everybody be honest about the TEA. And then if everybody looks at the numbers and says, wow, this is formidable. And after a while, the odds of it succeeding, then somebody like your friend, Dave, they have to give it up after a while. But if maybe the TEA says, well, you're kind of close and it requires a little innovation here and here, well, maybe it's worth the team going for,
Yeah, but neither the chemist or the chemical engineer typically make that decision. That some management person on high who's in charge of the budget is going to be the one that says, well, you haven't made a good enough case, or the budget isn't there, the company's changing direction.
Yeah.
So, but you're right. We need to find answers if we can.
So David,
go ahead. I'm sorry. There's a comment on for Dave. The thing that could have happened, and to your point here, Keith. One, you could say, okay, this has a problem because of impurities. Okay, one, chemical engineer, can you figure out how the hell to end up getting a better purification on this particular feed stream? Mr. Chemist, can you end up figuring out any way to end up desensitizing the catalyst to the point where it's not going to end up basically taking a hit with let's say ppm of impurities? Okay, maybe they reduce that to ppb. Okay,
Yep.
maybe we can get something else to say we can fraction or get some kind of a cleaning process so you can come down into that particular range. And that's but you have to do that, and that has to say, here's you. Let's see what you can do.
So in other words,
David, I have a question. With regards to the super acid, and you talked about how when it went into pilot, the impurity was affecting the performance of the super acid catalyst. It's because of the impurities that were in the feedstock. The big question that I have in listening to your comments on that is, wasn't there a moment where some of that feedstock could have been taken into the research lab at the bench with the chemist and run at a large enough scale to kind of give you a heads up that there's going to be a problem?
No, you're right. And I mentioned that in my slide, that
Right.
was the thing we should have done.
Right.
Absolutely. Yep.
Okay. So then following up on that, why wouldn't there be support to do that? I'm just puzzled, because the big question that I have is, I mean, we're on the same page on this, but it seems if you had that issue, then you wouldn't necessarily have to spend the capital money to form the pilot plant. You can maybe address that, going back to Harv's point.
You're
address
right,
that
but
problem earlier.
nobody was wise enough to think about it at the time. They didn't realize they were using super pure normal butane in the lab.
Right.
So, hindsight is great.
Sure.
We should have had it.
Sure.
But then again, maybe, as Arv just said, we could have treated the feedstock and gotten the impurity level down to an acceptable level. But the company decided to give up on long-term research. Just at the time we were doing this and starting to get pretty excited about it.
Yeah.
Very disappointing.
Yeah, I could see that. I mean, the technology sounds great. And it sounds like at the end of your story there, it did find a purpose in the long run.
Yeah.
So somebody probably solved the impurity problem.
Right.
But I don't know that. Yeah.
Thank you.
Any other questions?
So Dave, basically, it was a matter of not actually using actual real world refinery samples. I'm just kind of surprised about that. I mean, I would always want to use the real thing.
Well, Keith, I just said hindsight's wonderful. We didn't. We should have, and next time somebody's going to do that, right?
Gotcha.
We didn't. We just didn't think about it.
And to some degree, that's understandable. If you basically are sitting there doing a super acid catalyst and you just don't know what you're going to do, well, you're going to take a butane and see how the hell it works. Okay, you're not going to say, well, I know it's going to work, so I'm going to go out there and now get myself a refinery butane stream to come up and do it. And second of all, that butane stream, if you went to Marcus Hook, it would have trace amounts of sulfuric acid in it, okay, plus some other stuff. If you go, let's say, up to Philadelphia, it's going to have many traces of HF in it, okay? Right. Well, they're two different impurities, okay? Sometimes, so that, and if he's just doing fundamental research at that point, you probably would say, I'm going to see if it works for purity before I start goosing it up with impurities to see what happens. But having said that, if it looked good, yes, then if you're going to say economically, we're going to put it here, it's going to get this butane stream. It has this amount of it. What do we have to do? And that's would be a question.
Right.
And I mean, we do it. We do now for getting sulfur can be any kind of sulfur compound can be a real killer for a lot of processes. And we can get down to super pure levels in sulfur. So some of that stuff is doable. It's just, you have to do it.
Yeah. Yep.
So that's my 2 cents anyway. For you, august group of gentlemen.
I have a question.
Anything else?
Yeah. This group, I think, is deep in the Philly refineries. Any perspectives on the demise?
Well, that's a whole story in itself. We could talk about that forever. I think Sun was at one point a major company, and its headquarters was here in Philly. Yeah. They were a fully integrated company with exploration, production, refining, marketing, R&D, a pipeline, tar sands up in Alberta, the first company to develop the tar sands because the Pew family felt this country was running out of oil. And there's a huge deposit of this crappy stuff up there. Huge company. And then for reasons I'll never understand, I think part of it is our refineries, and we had 7 at one time, could only run sweet crudes. Every 10 years, it'd be a major study. Are we going to invest the money so we can run heavier crudes? And Sun never put that money in. And then for a time, Venezuelan crude is very heavy. They built a refinery in Puerto Rico to run Venezuelan crude. And then the Venezuelans nationalized the crude supply.
Yeah.
So Sun did not have it at Puerto Rico any longer. There are probably a lot of reasons. I mean, if fracking had occurred maybe 10 or 15 years ago, in time for Sun's refineries to see that their refineries that would fit well, we might still have refineries. But there are no operating refineries in the Sun system. The Sunoco that you see out in the service stations, there's 7,300 of them in this country. It's all fuel that's bought and manufactured by other refiners. Sun is not a refining business anymore.
But
It's
Dave, you could end up the fact that the child, which happened to be Suncor in Canada, is probably one of the largest corporations in Canada.
It could have bought Sunoco, yeah.
Yeah, now they can buy. We could have bought Sunoco for
Sun's foolishly sold it.
Yeah, part of that particular. Well, now, in answer to your question, are you, Freddie, you asking about hydrocarbons in general or what?
Was it ultimately a maintenance issue that the pipes got too thin?
I'm sorry?
Oh, you're talking about Toledo refinery? I mean,
No,
Philadelphia
Philadelphia.
refinery?
Why did Philadelphia blow up?
Oh, you mean the HF, the HF problem?
Yeah.
I don't know that specifically. I just have basically, this is, stuff that you just heard on the QT or stuff as you read.
Well, it's a badly corroded piece of pipe. That was a piece of pipe not specified for the service it was in.
It was a maintenance issue.
Yeah.
Okay.
Well, it may be an original design issue. They may have used a material
Both.
that was not suitable. But it's gone, and it was probably in a bad location to be in the heart of Philadelphia or close to it. So it isn't the worst thing in the world that it's not there. It's just disappointing to those of us who supported it in the past.
Yeah.
But, we move on.
Yeah, no, this is a special group of people who might fundamentally understand things. That's the only reason I asked.
Yeah.
Yeah.
Maybe a chemist put that pipe in instead of a chemical engineer.
Yeah, well, one of the issues you got to look at here is that you've got, when you start building these plants, and this is a little bit, we're going tangential here, but just as a point, there was a big, very bad fire down in the Exxon Baton Rouge refinery a couple of years ago. You probably read about it. I mean, it took out about a third of half of the refinery. And that was due to somebody basically putting in the wrong metallurgy in one valve, in one piece of one unit. Okay, it was a coker that had that should have had a specified of a valve of a special metallurgy. Someone probably decided, what the hell's the difference? I'll put it in. By the time I go, they'll never know it, and who cares? Well, you can see what the hell happened. And at the same time, when some guy now comes in and nicks the pipeline with a backhoe and figures out he's going to just, put the dirt over there and say none, then the catalytic protection is gone. That pipeline now has a problem, and it's going to end up basically corroding. And you're going to get, if it's a real pressured up, you're damn near going to have a corrosion problem in there. So those are tangential issues, not to this particular discussion, but things you have to end up worrying about, and that can be major.
Well, okay, so this was probably mid-career for you, but back in my childhood, I did a summer at Chambers and was associated with the Freon operation. And so they did a lot of tantalum stuff because that was a good way to handle HF. And I'm just wondering, maybe they needed a little bit more tantalum in Philly, but oh well, whatever. To Dave's point.
We had, having run an HF plant, okay, there was a couple of things you had to end up knowing about it, okay? First of all, if you keep the acid strength up and things are clean, okay, things are good. If your acid strength goes down, okay, and you put it in there, you can almost watch the damn plant disintegrate in front of your eyes. It's especially true for sulfuric acid, okay? And HF alkylation, which has a big deal because it does not require a refrigeration compressor, you have to have clean feed, i.e. no sulfur. You have to have clean acid, and you have to have clean, the circular isobutane had to be clean, the feedstock had to be clean, and the acid had to be clean. If you basically did that, it would run like a top. If you violated any one of those constraints, okay, you had issues.
Fred, just to answer your question in another way too, Philadelphia refiners had an obligation to purchase ethanol credits if they didn't blend ethanol in their fuel. And refiners really hurt. This really, I think, put some of them out of business. They just couldn't afford it. And the Philadelphia refinery was losing money hand over fist because of that. So I think the problem is certainly serious, but I think the ethanol mandate,
Which is
Yeah.
probably
That's
part of
something.
why they under-maintained it. Or
Well-
under-measured or under. Hey, one final thought. There is a lot of wisdom, like the Dave Vahlsings and the ARV, a lot of experience expressed in what you're saying. We've gone through cycles of 2008 and the COVID thing and blah, blah, blah. How's the pipeline looking for chemical engineers?
Say more. What do you mean? How's it looking?
Okay, so I mean, there are a whole bunch of people in the graduating class, and when the graduating class graduates, what
They go into Denver.
knowledge, capability will still be in the system before lithium batteries simply take over?
Well, I don't want a battery in the airplane I fly. I'll tell you that. There's going to be a place for hydrocarbon fuels for quite a while.
No, I'm not undermining that. What I'm worried about is whether or not the professional proficiency pipeline is being well enough fed and well enough nurtured so that the wisdoms that you guys have.
That's
can
a
be
great question.
replicated.
And I think the problem is companies are afraid to hire anybody and keep them for 33 years, as they did to me,
Yeah.
with me, because the loyalty for employees is not there, and the company loyalty to the employees is not there. So if you don't work for X years, at least 10 years, and become knowledgeable in your field, and have mentors, and that's not happening. I think companies are letting folks go, and people are leaving.
Your slide of your experience, I mean, that's classic of what we need.
It was. I don't think it's going to be anymore.
I
Can you
totally
imagine?
agree.
You imagine
that's
a
what
company
scares me.
taking a graduate chemical engineer and putting him in a lab for 4 months just to learn how the tests are done today?
You know what they're going to want to do is biotech.
Look, let me give you a point here where I do most of my consulting work for the last 20 years, okay? It's basically getting out kids, okay, that don't know their tails from first base out from behind their computers out in the field. Now, why? Okay, and Dave basically said it. Someone comes up with a cost cutting, okay? You get somebody in there, they figure out, well, all I need is the operator and the plant and the feedstock. I don't need engineers because the thing is running. And for
And
1
they're
week,
expensive.
couple of weeks, so forth, you're good, okay? Then all of a sudden, they end up figuring out, after they do that for a while, gee, I need to expand. There's nobody there. The other guys are not there. So now what are they going to do? They hire a bunch of kids, okay? The kids come in, and they, as Dave said, they have no oil in their shoes. They don't know squat, okay? So now you got to get them. So now they're kind of hidden behind their computer screens and their little offices doing things. And we have to get them out from on the office, drag them out. So they have good information there, And having come up through that, I can tell you, but I also knew the other part. I have to get them to say, you're going to get some information from the guys who run the plant, okay? That is not, that information is not going to show up on your screen, and you have to know that. And then you're going to start becoming a real person doing this particular work. And that's right.
Let me mention one more thing Sun tried to do a number of years ago. They went out and selected the top people from universities and brought them in with a 3 9-month assignment deal where they would work in 3 different parts of the company for 9 months in each location. And you know what happened when this was all done? These guys or gals got so much experience, they were sought after and hired away.
That's
and
right.
Sun stopped doing it. Sun stopped doing it.
Yeah.
This was probably about 20 years ago.
Yeah. Remember.
Joe,
So,
Mike,
you know, and when I started,
need to
would you
run with
point
that.
out, when I started in the refinery for 2 years, I went out in the plant every morning, took a sample from a reformer of the hydrogen to test its purity, went into the operating room, wrote down data on an actual piece of paper, and prepared a report, a daily report on the operations for 2 years.
And survived some hazing while doing it.
Oh, I did get plenty of that. Yeah.
And now they would call that high touch.
Yeah, that's right. You can't do that anymore.
No.
Somebody mentioned me in a little bit.
Joe, I'm just thinking, this is a land of threat and opportunity. Focus on the opportunity.
Mm-hmm.
You can be an evangelist for learnings of, I'm not sure what the learnings might be, but I'm a little concerned that stuff might fall apart.
You're not the only one.
Yeah.
The
You know, I
schools
just
are
wanted to
turning
kind of,
out more and more young chemical engineers, though.
Hi, Alan. How are you?
I'm fine. I'm glad to see all you guys. I haven't
It's
seen
good
Arv
to
in
see you.
years.
You're looking
Hi, Arv.
good.
How you doing, guy?
Good.
The
good.
R&D
I now
lab.
in Blacksburg, Virginia, and so I get to go over to Virginia Tech every so often.
Nice.
Good.
And I'm going to do some coursework over there in the fall. But one of the things which has impressed me is they had 105 students graduate in chemical engineering. And I thought, like many of you, hey, where are these people going to get jobs? And that's the thing is, a lot of chemical engineers go into medicine. Okay, that's one of the things.
So I did see a recent CNE news, and the hiring statistics for both chemists and chemical engineers over the last year has been pretty decent. So please don't, Dave's absolutely right. There's no loyalty to companies, blah, blah, that's all true. But at least initial hiring statistics are not too terrible at all.
No.
Well, it cycles too. It definitely cycles. I mean, when I went to school to become an architect, yes. But at the end of your first year, you have to make a choice. And I had a senior chemical engineer who was flying all over the country with great job offers. And being the greedy guy I am, I decided to be a chemical engineer. And I graduated, and guess what? 3 years later, it was a very poor time to get a job. A large number of my classmates could not get a job. And because I'd worked for Sunoco in R&D for the summer, they gave me a job right straight out of school. And I was very fortunate. But kids with much better grade averages than I had could not get a job. So it's a cyclical thing. I'm sure for chemists too, but for chemical engineers, the market ebbs and flows.
That's the right path.
Marv may want to bring it to a close.
Follow the money. Follow the money. There's more money in our world.
We'll get in trouble if we keep this up. Yeah.
All right. Hey, great discussion, guys. I appreciate it.
All right, thanks.
Great seeing you guys.
Good to see you, Alan.
Yeah, thank you.
Nice to see you, Dave.